And along with all of the people, we are part of the I'm part of the committee organization of swim. So before start, I would like to apologize because I have a little flu, but I will do my best. So I would like to, if you have any questions, please interrupt me. I will be attentive to the if somebody has any questions. So for today, I will give an overview about diffusion imaging. So yeah, let's do it. So first of all, in terms of overview in this presentation, we will mix a bit about the material about the diffusion MRI, and also we will see a little bit of what is the main steps about when you want to process the images. So mainly the first part, so we will know to what's going on with diffusion, how the principal key points about these kind of images, and also what if when you process it, what do you want to expect, or what result do you will have, and what does it mean, and what you can do with all of these kind of images. Yeah. So first of all, as everybody knows, that the diffusion image is measured the random of the water, the movement of the water molecules, that the Bromian movement. So, for example, if you have a water molecules that is hits in within an environment that have no restriction to movement, it's like free diffusion. Like you see in the example about this glass of water, you have because they have any restriction the water molecules if you evaluate in the first second and the second they have free movement. However, this is not always the case because we are measuring different kind of structures, like for instance the brain, because you have some structure that limits the movement of the water molecules. So that's the reason we can measure this invisible property, and we can also transform into signal, and also we can evaluate the water movement. So mainly the same example. So you have your glass of water, you have something it's called isotropic diffusion, because normally when you have these kind of molecules, they have two main properties. The first one, they have free movement. And also there is one important thing that you measure when you're doing diffusion is like you measure which is the main direction of the water molecule moves. So for example, in this case, because they have no restriction, the water molecules will move to any direction. However, we will see it is not always the case in the whole part of the brain, because normally you are some water molecules are condensed in some structures, so it doesn't have free movement, so they have one movement in preferentially. Yeah. So this is the case. For instance, if we talk about the brain, for example, we can take for example two main structures. We can talk about the ventricles and also the myelin sheaths. So the myelin sheaths, they are hydrophobic. So normally all of the water molecules across the axon will have one direction in preferably. So mainly if
Oh,
you of course they
Christian,
have
1 second, Christian. Can you click like for full screen? We can see your full screen.
yeah. Do you see
Your
my screen?
we can see your screen, but we need it to be full. Like it has to
One
show.
second.
Yeah.
So
Can share the screen and show slide.
do you see
We
the
can
the
see
full
your
screen?
screen. Yeah.
But
We
you
need
see
to.
the full.
Yeah, the full. Yeah, the full.
It's okay right now or not?
Not display setting. Yeah, full
One second.
screen. Oh, it's out.
What about now?
Oh, no, no, we can't see your screen yet. Oh, good. Now we can see it now. Good.
Yes, yeah,
Yeah.
yeah. Yeah. Thanks, Harrison.
Yeah.
So mainly, giving a summary. So if you have the water, the case of the water glass, so they can have free no restriction at all for the water molecules, so they can move in whatever direction. And also when you have the brain, it's more restricted. So for example, if For example, if you have two compartments, one is the mining sheets, and another is the ventricle, the several ventricles. So in this case, the axons moves of one direction of preference. So they have mainly all of the movements have in one direction, but additionally they have another one that is like perpendicular of them. So we like to say in the axons we have in terms of the mean of the movement, you have an ellipsoid than a perfect circle that I showed you before, you know. So mainly in the axons, you have some like a ellipsoid because the movement is more like direct for one in preference for one direction instead of if you evaluate, for example, the ventricles, they move to any direction. Any questions so far? Yeah. So
I think
mainly,
we're good.
yeah, perfect. So mainly how we measure this the water molecule diffusion. So I divided this in three main steps. First, you need to evaluate in two moments because you have the water. Imagine you have a water molecule in one time you measure in one time. Another you need to measure in another time in a second one, and you need to evaluate the difference if they have movement, if you have any difference because of the second part of the second measurement of the first, or they move a lot. So mainly you tag that difference of the movement with a gradient. Secondly, you use another opposite gradient to evaluate this difference, and later you read the signal, and later you resolve some equations and you quantify this difference of the movement. So, like, how do you do the first step? We tag the image because, if you remember, you have this equation about you need to tag these water molecules with you because in terms of you put one gradient in this step, so you need to have a phase. This water molecule needs to have a phase. So the equation that govern this phase is with the gyromagnetic radio, the position and the time, and in all of the molecules they have one different to evaluate or differentiate. You have one type of gradient, so let's have one phase, and it's like this. For example, this is water molecule that have no movement. So imagine you have one water molecule that it doesn't have restricted diffusion. So if you measure in the first step and the second, they have no movement. So what does it mean? So as I told you, you apply one gradient. So yeah, they have the phase. And secondly, we apply another gradient that they have the negative part and is equivalent with the first one. So what happens? So even if they imagine like they cancel out the signal. So because what this happened? Because the movement of the water molecule, it doesn't have a residual phase. It have no motion. So if you have the first gradient have the water molecule and the second gradient cancels it, they have no signal and you can measure that. Yeah. But yeah, I will
Don't
continue.
worry, I'm muting them for you.
Yeah, thank you.
Yeah.
Yeah, and the second part is, for example, this is what happens mainly in the white matter, for instance. But this is an example of what happens in the ventricles. We have to have free movement. So what happens if we have in this diagram below? So we have one water molecule in this located in this place is XA, and you have the same gradient. And afterwards, you apply the same gradient like negative, and it's in other place. So that doesn't mean the water molecule doesn't perceive in terms of time the same gradient. So that's the reason they can have a different signal that is not zero. So you can measure it. Yeah. And also that's the main you need to forget this is the main point of the diffusion sequence that was developed by Stengel and Tanner in the 60s. So mainly it's like a spin echo T2 with two grade, it's an API, and also you need two gradients of the difference because you need to evaluate in all of the environment. The first gradient, you have the phase, and the second gradient is the opposite direction. They evaluate the difference of the movement, And when you have a restriction movement, it will be zero signal because the gradients cancel the phase. And if you have a one molecule that moves like free movement, they will have a different value than there is not zero. Yeah, this is the main point of the diffusion. Yeah, so continuing, and also we would like to measure. We don't need to forget that our brain have a three-dimensional structure. So we like to evaluate the movement in the three main directions in the space, like X, Y, and Z. Because of the water molecules, they have different movement in terms of the time. So we need to evaluate this kind of movement in different directions. And how we can do it? Because for example, how we can in the console, how we can manage this duration of the gradient is this the all well known called v value. The v value is a measure that you can change in the scanner. So mainly is the strength of the duration of the diffusion gradients. And you need well, how is it do it? Because it has the difference between the one gradient and another one, if you see below in the diagram. So mainly, you need to evaluate that when you have a v-value, we have higher values. You can evaluate in terms of the time more water movement. For example, it's like you have a rule. For example, if you have, I don't know, you can measure only, for example, imagine you have a rule, you can measure 1 kilometer of movement. So everything is within 1 kilometer in movement, you can evaluate with a v value of 1,000, for example. But if you have a water molecule that is 2 kilometers, you cannot measure it. So this is a trade game because if you have more v values, you can evaluate more water movement, but however, the signal doesn't recover in this time because it doesn't see another 90 degrees RF pulse, so you have less signal. And this is what happens here. So this is an example. You have a V0 that in the base is a T2 image, and later you can evaluate what happens with normally when you apply a V value of 1,000, that is the standard about brain imaging. But if you have more V values, you will have less signal. This is very useful, for example, in prostate images. That, for example, you acquire two main diffusions, one between V0 and V1000, and another one is V0 and 3000, and so on, to evaluate also the main dropout, and also if you have another disease that have more free water movement. Yeah. And this is what happens when you have, I told you before, when there's no gradient applied. So mainly, we don't like to forget that the DWI, the V0 is like a T2, you know? You have, of course, we have less resolution than a T2 spin echo, and it is a T2 API. But when you apply this kind of directions, so mainly when you would like to apply to at least you need to have 3 dimensions to evaluate the free water movement. So you can have you can evaluate how is the movement on the 3 directions, and also you can evaluate different structures. Yeah. Any questions so far? No? Any questions within the chat?
Within the
No?
chat for now, no. I discovered that I was okay. No, no.
Yeah.
This
So yeah, thanks, Harrison. So this is the first part. The second part, I will explain because I told you that you will use 3 directions to evaluate what's happening in the 3 directions of the white matter. But and now the second part of the presentation, I will talk about a mix about how we can process this image and also what happens when you acquire more than 3 directions. So mainly, I will mix these two main contents. So mainly when you like to evaluate or you would like to analyze this kind of image, you have 6 steps. Yeah. First, you do the acquisition, like I told you before. You see in the scanner the diffusion image, and you acquire with the v values, mainly v0 and 1000, and you can choose between different directions. If you acquire 3 directions, you have a diffusion image, to calculate the ADC, and if you acquire more than 6, you will have my bad, tractography. But I will DTI, but I will tell you in a second. After you acquire the image, you will like to don't forget some steps. So I will talk about right now about data processing. So mainly the data processing, you need to be sure that mainly you have two main images. You have the T1 because of course, since the diffusion has a low resolution, you would like to have another one like a 3D image of T1 or because you can complement the information. And also you can perform some image processing about that. And this is mainly one of the examples I use in this structure called VITs. VITs, it's like a standard how you can analyze the image, you know. So mainly you have two main folders, it's like T1 and the DWI. Yeah. And mainly in the DWI, you have these four kind of files, and that it's very important to know what is going on because you have the main diffusion image that is DWI.ni. Not .ni is like a format you transform from Daikon to Nifty. It's because it's a small Daikon format in terms of example that it's very easy to how to handle and wait less. You have the JSON file. The JSON file, it's only it's like a text that it's a log that they keep all of the things about the image. And you have the Vival and the Vivek. And this is very important because the Vival and the Vivek, you need to be sure that the Vival in this example, if you put only you acquire two V values, the first one is 0, and later you have the 1000. Yeah. And the Vivek is how are the gradients in the different directions. So this is very important because when you process the images, all of the scanner brands has different kind of properties that is very useful to know in the time when you process the images. Yeah, because sometimes I remember that Philips and Siemens they order this a little bit different, or General Electric does another way. So you need to be sure how to you need to figure how in which brand you are acquiring this kind of image, and later you can work with it. And with the terms of data processing, when you acquire this image, you have a lot of artifacts. So mainly in one of the artifacts, you have an eddy current. So it's a distortion about because you change a lot of the gradients to acquire the images. And also it's very normal to have some distortions in terms of the frontal temporal lobe because you have the sinus here, the frontal sinus. So mainly you would like to acquire, you have a processing in this kind of image to eliminate these artifacts. So mainly, as you can see, this is an example of a healthy patient. So mainly it's mainly you have this kind of image with the distortion, and you have some algorithms to correct it. And mainly, if you acquire some another image to evaluate how is the distortion in two directions, you can have this information and you apply it in this kind of brain, and you can have one corrected. Yeah. So this is very important. How to do it. So mainly is the main point of this part is to correct this kind of artifacts. Yeah. Because you need to remember this is an API. So an API has a lot of artifacts. And this heavy current artifact. So mainly with with different kind of softwares. The most famous one is called FSL. So mainly you can replace it, or you can fix it. And this is important. Why this part is very important? Because one thing, when you acquire your image, you need to be sure that there's a patient inside the scanner. Why? Because normally, in terms of the diffusion, if you acquire more directions, I will talk about later, or more B values, you will have more time because you have more images. But however, imagine if you're acquiring a patient about 10 minutes, it happens to me all of the time, you're acquiring an image about a diffusion image about 10 minutes, and the patient have a lot of movements. You need to be sure to see if the image is correct. If it's not, when it's possible, you need to repeat the image and repeat it and repeat it. Why? Because if you have the patient have a movement, you also have this kind of artifacts. Because one thing is very different if you acquire an image and later when you process it. So they have a consequence. So it's very important to know these kind of steps because you would like to have a clean diffusion image. Yeah. And this is an example that has this is an example without movement. So they have an eddy current artifact, and this is after the correction. So in terms of this kind of artifacts, you miss, for example, 3 kinds of slice, and here you have the whole image. And that's the main point. If it's very important to inspect your data, it doesn't like takes you, I don't know, 30 seconds to see the image, but you need to be sure that all of the images is well acquired and well processed. And how we can evaluate this brain, I was talking about the whole presentation in terms of the microstructure. I would like to give a short overview about what is a tensor, because normally I told you when you acquire a diffusion image, you mainly have 2 values, and you evaluate the gradient in 3 directions of the space, and that's the standard to evaluate the brain. But however, what if you would like to, because the brain is a 3D structure, so you like to measure what is going on between all of the directions of the brain, yeah? Because more of the brain is not like in 3 dimensions. It's more like we like to evaluate the whole brain and the whole direction of the movement of the water. So mainly you need to evaluate as a tensor. So sorry. So the tensor is like, well, it's a mathematical measure. So you have the scalar, is a single number. The vector is a list of scalar, this is a list of numbers, you have one direction. A matrix is like an array of different numbers and rows and columns. And the tensor is, imagine like you have a huge matrix, we have 3 or 4 dimensions, yeah, to represent of the water movement. Why this is important? Because we resolve an equation to evaluate the tensor, because if you like to evaluate what is going on in the whole brain, you need to acquire more than at least 6 directions, because you like to have this tensor. So it's called the diffusion tensor. It contains every voxel into 3 diffusion tensors. So mainly this matrix describes the water diffusion along this X, Y, and Z location. And you need to remember that the diagonal is the main point that evaluates all of the voxels direction. And the another one, they help to resolve the equation, and they relate to another directions, and you have more information. Yeah. So mainly, I would like to say that the diagonal is the main axis of the voxel, and the another ones helps you to have a correct measurement when you resolve this kind of tensor. And this is how we saw it, because you have this tensor about the 3 main diagonal values, and also in terms of one voxel, you can evaluate in which, because in terms of X, Y, and Z, which is the main direction that this water molecule will have a movement, in terms of it's an ellipsoid or it's a perfect circle, etc., etc., etc. Yeah. So mainly you have the diffusion water images. You would like to have a fit the voxel, yeah, in terms of the water movement. Later you have the tensor, because you would like to describe this water movement in a complex way. And later you have this representation in terms of, in this case, for example, if you have one tract that is straight, they have an ellipsoid form. And this is what I would like to talk about, because you will have this tensor, it's like an ellipsoid, and you can measure in different direction of the brain, yeah, of the gradients. And the tensor is the same information. Normally, if you evaluate, for example, if you have brain vertical, you have 3 diffusion. So we have a spherical tensor. So it's quite different when you do and have an anisotropic water movement because these tensors will be elongated. So they have one main direction of preference. It is normally the case in general of the white matter. So this is the same information. So mainly when you have this ellipsoid, you can evaluate, you have a tensor model and you can evaluate the diffusivity of in the different directions of the space. Yeah. And normally, this is important because now with this tensor, you have two main parameters. You have the eigenvectors and the eigenvalues. The eigenvectors is the vector per se, is the direction, and the eigenvalues is the scalar, is the measurement of your eigenvectors. For example, in this example, you have three eigenvalues, and this is three main eigenvectors. And the first eigenvector is they have the scalar the highest value. So mainly they have in general they have in terms of ellipsoid form. Yeah. And why this is important? Because when you have these eigenvalues, you can have different parameters. You can evaluate with your diffusion with at least 6 directions. So we're gonna evaluate I don't know if you heard about these main parameters, is the fractional anisotropy. I will talk about soon. Is like how it's between 0 and 1. So how is this form of the water movement? It's between 0 is like a perfect sphere, or it's 1 is like an ellipsoid. Mean diffusivity is the mean move of is the average of these three eigenvalues. The axial diffusivity is along the main axis, is like axial, and the radial is perpendicular. As a tip, mainly in most of the diseases, the most evaluated ones is the FA and the MD, and another one is very useful to evaluate what is going on with the brain. But mainly when you do research or when you want to report something, mainly all of the people they use more FA and MD. Yeah. And this one I talk about the fractional anisotropy because the FA summarizes how the voxel is directional, it's anisotropic or is uniform isotropic in terms of the three eigenvalues. So mainly you have the ventricle, you have an FA value of 0 because it is a perfect sphere. We have a corpus callosum, so we have one direction in terms of XC. So we have mainly not a score of 1, but mainly it's close to 1.0. And also when you have these the equations, and this is how the images are. So mainly when you have these three eigenvalues, you can calculate the another different measures. You have the mean diffusivity, radial diffusivity, and axial diffusivity. And also you have this color map that is normally to evaluate how is this a standard about the colors, what is the directions. So mainly this is very useful. Mainly the most useful ones is the FA and the mean, but the color map is very useful to evaluate some kind of diseases, of reproducibility of the brain, etc. And so yeah, mainly, so you have you first, I would like to do a summary. So mainly we talk about how to acquire the images, later how to process it, and later how we can evaluate that. Because you have the brain, for example, you have this FA of the whole of the brain, but how we can measure the corpus callosum? Yeah, we only would like to have the corpus callosum, and the rest it doesn't matter. So how I do it? Because you have two main ways to how to do it to analyze this. For example, you have a lot of images about a lot of patients. I would like to write the corpus callosum. You have two main ways. The first one, if you segment it by manually, mostly all of the neuroradiologists do it, but it's hard to do it because every brain is different. So mainly to segment all of the corpus callosum, it could be not reproducible as well. The another one is to nowadays with the help of AI, for example, with deep learning toolbox, we can automatically segment the corpus callosum, but however, you need to know doesn't exist every deep learning toolbox to segment every part of the brain, or maybe it is, but you need to evaluate, and one is like very validated and is very useful to your case. But for example, there's a lot of AI toolboxes to segment the brain, but to segment a brain tumor, but every toolbox does different because they segment the tumor or the parenchyma of the tumor, etc., etc., etc. And another way that is more like classical is how to use atlases. And mainly when you have an atlases, you can download in internet. For example, this one is of John Hopkins, so you can have in blue the corpus callosum. This is a white matter tract. And the thing that you do with mathematical processing, you download this atlas and you multiply, but you apply above your FA map, for instance. And later you can have the main FA value of all of the structure in all of the patients. And normally you can have when you acquire all of the images, you have different kind of metrics. Then you can evaluate of your different kind of maps. So I will talk some of them. So mainly you can have this, it's called tract-based spatial statistics. So mainly you can have all of the FA maps. You are aligned in a common space because every brain is different. So mainly you transform, mathematically speaking, all of the brains in a common space, and later you can evaluate the mean FA. You have a skeleton of the FA map, and later you can evaluate different kind of measurements. And you can have a voxel wise, and you can this is in red color, which is the main important voxels that are has statistical differences between two kind of groups. Another one is to evaluate the microstructure maps as well. So it's like I told you, this one they evaluate the skeleton of the FA and MD because in different kind of patients as well, in some kind of diseases. You need to be sure that different diseases has different behavior in terms of the diffusion. So for example, it is very well known, if you have multiple sclerosis, you will have a decrease in FA and you have an increase in MD, for example. But not always the case in every disease. So mainly when you process it, and you can have all of the values, you need to have a logical result. Yeah, it's not like to process all of the images, you have everything, and you can mix it and have a result. No, you need to have a coherent result with your disease. Yeah. And also, you can evaluate different white matter tracts. For example, you can have different white matter tracts, and you can evaluate all of the values that I told you before, especially in different kind of diseases. Yeah. And you can have this advanced, because normally when you acquire the image you calculate the tensor, I told you that this is called diffusion tensor imaging. Yeah. So it's mainly when you say you have a diffusion tensor imaging, is mainly you have 2B values and you have at least 6 or more directions to evaluate this kind of space. But mainly you can have another advanced diffusion model, is more like in research, like NODI or whatever. It's more like sophisticated terms of how to represent the white matter molecules, because normally the diffusion tensor imaging, you can, in this case, you can evaluate, you represent as an ellipsoid, but normally not all of the white matter tracks represent as an ellipsoid. Mainly when you have a subcortical or cortical brain image, they have different orientation, and it's very hard to measure it with diffusion tensor imaging. Yeah, so you have more advanced diffusion models. And also you can have a tractography. So mainly you can reconstruct all of these paths. So mainly you can evaluate, you can perform a tractogram. So mainly when you can perform all of the tractogram, and also when you have an atlases, you can evaluate specifically which are the main tracks you would like to study. Yeah. And also, for example, you have in this case the tractogram, you have all of the connectivity, for example, in this the whole brain, but you would like to have, for example, in forceps or any in particular. So you can have an atlas in this case, and also you can evaluate only how is the connectivity between two these along of these areas and along of the tracts. This is very useful, for example, when you do brain tumor imaging, because, for example, the brain tumor, they interrupt this pathway. So mainly we like to evaluate how is the path, so how is interrupted this pathway between two brain areas, and how is the connectivity, and how is the neuroplasticity of the brain, and so on. And also you can have a structural connectivity that I told you before. So mainly is could be represented in this matrix, in this correlation matrix. So mainly, for example, if you have this part of the what is the connection between the 17th and the 33rd, or between the 17th and the 34th, you can evaluate how is the connectivity within these main structures, because this you have the diagonal always it represent to compare with how is the connectivity within the same value, so they have one color, and the two other sides are the mirror of each ones. So mainly, if you have a color bar and you represent the yellow one is the have a strong connectivity, and the blue, when it's more blue, it have less connectivity, and you can evaluate how is the correlation. Because this would be very useful in this case, because you can represent how is the connectivity and how are because in terms of connectivity, we have a lot of information, and mainly you can evaluate some information that is not useful. It's like in terms of statistics we call collineal data. So mainly we like to evaluate a few brain areas, or we like to separate in different behavior in different clusters. So this is very useful to evaluate the behavior of these connectivity. Because, for example, we can have two main because, for example, you have two main patients who have with lower grade brain tumors and high grade tumors, and later you can evaluate the connectivity, for example, and you can evaluate the difference in these two structure connectivity matrix. You can evaluate which are the best brain which have or stronger connections or not in these kind of maps. And in terms of ending this presentation, you need to remember, because when you start the diffusion, it's very important when you acquire the image. You need to remember that the patient moves a lot, because normally these kind of images are it length more than 5 minutes at least. It's very important when you do the data processing. You need to reduce the noise that we saw in the eddy current. Later, when you do the image analysis, we like to evaluate because you decide which kind of equation do you like to modulate your brain in terms of, we talk about the diffusion tensor imaging, and later you can have this kind of maps like FA, mean diffusivity, axial diffusivity, and radial diffusivity. And later, how you can evaluate this kind of group of analysis. You have different kind of toolbox. You have one to evaluate the skeleton, or you can have download an atlas and you can evaluate them, or you can have this kind of matrix, connectivity matrix. You can compare among different patients, and you can have different statistical inference. Mainly, you can evaluate to the student, or you imagine have a machine learning model. You can evaluate the difference between for classification, for example. And you need to remember that you have different toolboxes to do this. For example, you have one is MR-Trix, for example, FSL. Is very well known to how to process this kind of image, but FSL only works in Linux and Mac. And mainly, so what I do now in general, I would like to mix toolbox because one kind of toolbox has advantages, another have disadvantages. So we'll try to use the best of the whole worlds, and later you can have a nice kind of images. That's all. I'm open for questions.
So mine is not a question, but
Okay.
more of like a contribution. Um, so I know we are doing PulseSec this swim series, like this 2026 swim. Is it possible we integrate DTI in PulseSec?
This is not. This is not like easy as you say because in pulsec pulsec is like a because when you have the chance because you when you work when you work in the scanner mainly you have this is like closed scanner because you cannot change some have some restrictions and in the old days you can have some programs you can hack the scanner so you
Okay.
can create an image and you can do whatever you want and normally it's like it's very difficult because every brand of scanner has different programming languages.
Hmm.
For example, Siemens has C++, and Philips. I used to work in Philips with Pulse programming. It's a little bit hard because they have a own language,
Okay.
so it's not well documented. Yeah. Nowadays, Maxim is like a researcher from Germany. They create PyPulsec, so it is like a Python code, or it's more friendly. So mainly you can run a code in Python and you can hack the scanner with a sequence. Normally, it is very easy to do. It's not difficult to do, for example, T1 image, gradient echo, and so on. But if you want to do diffusion, you need to program, for example, in this case, you have the same program about the T2 API, but you need to program the gradients in different directions.
Hmm.
So you need, in this case, for example, you have your Python code in terms of the T2 and spin echo.
Hmm.
And later you need to add in some part, you need to declare a gradient, the two opposite gradients, and also the different directions. It's not
Okay.
like, what I mean is it's possible, it's not like straightforward.
Yeah,
That's somebody,
I got it.
another,
I
another
got
example. If you do an fMRI,
yeah.
if you do an fMRI, I program it, but it's quite difficult because normally you do a T2 star, but you need to evaluate the volumes and you need to program the volumes.
Yeah.
So it's like what I mean is not like some sequences is more challenging because two main things. You need to know to program Python and you need to the behavior of the sequence. What I mean is not impossible, but
It's
it's a little bit
difficult.
it's difficult. Yeah, it's not
Yeah.
like for example a T1 or T2 is not easy is easy, but another one is a little bit difficult.
Yeah. So the reason I asked that question is because I am I am a medical radiographer just like you, but you deals more with, you have gone as far as doing image analysis. And because for the swim participants this year, we are basically going to be showing them PulseSec and then research methodology so that they are able to, produce good images that are research worthy, that they can publish in A plus AA journals and so on and so forth. What Christian has done today, just for the swim participant, we see that he moved from image acquisition into image analysis. And for some of you who are interested in um, who are interested in analyzing images from DTI, because basically everybody will not do the DTI. Me, I do more of ASL and DSC imaging and image analysis, image acquisition and analysis. I also acquire data for DTI. I know not all systems can acquire that how would I call it? this one by one millimeter voxel wise imaging when it comes to DTI. So we are hoping that we are able to show you some of the requirements that you need to acquire these images when you're acquiring it, so that when you are running your analysis to present in these journals, it's a little bit easy for you. You are not getting to deal with a lot of artifact and any of those stuff. So if you want to basically create a niche for yourself and go with what Christian is doing, you should know what you need to do in terms of image acquisition, and then what you need to do in terms of image analysis for DTI. So Christian has given us a hint. It might not be everything you need. If you need more question and you are interested in going into image analysis for DTI, I think Christian is open to guide you through, because there is no how you want to publish in high quality journals, maybe ISMRM, ESMRB, and so on and so forth, that you are not going to generate images. And thank God for AI in our generation. It has made image analysis a little bit easier compared to those who were coming from behind. So we hope to see more of this in the coming weeks. But one thing you should notice in this year's film is we are not just dealing with image acquisition. We're also going to be dealing more in image analysis, helping text go beyond just acquiring images and do more. That's for me. I don't know if anybody has any question. You are free to ask before Christian takes and then our friends in Asia is already late night and we don't want to keep them so long. All right, any question?
Any questions?
Hey, Christian.
Yeah.
Yeah.
I have a small question. Like, thank you for your presentation. It was great. I have a simple question. Like, what